Okay, everybody, thank you for coming. I'm very happy to introduce Marco. I know Marco for a long time. Marco is a cosmologist. He did his PhD in CISA, working with Paolo Creminelli. Then he moved to the Institute for Advanced Studies and worked with Matthias Saldariaga for his first postdoc. After that, he moved to CERN, and he's currently still at CERN. He has a junior position there. And the good news is that at some point in the near future, Marco will be becoming a professor at University of Florence. So he'll be moving to Italy back, returning to Italy, let's say. Marco has worked on many different topics related to cosmology. He started from inflation, but then he moved to the large-scale structure. And I think his main goal is to get accurate cosmological parameters from the data we already have and to predict what we're going to know about, we're going to learn in the future. And today is going to tell us about several things. We're not sure what.
Me neither. Yes. Thanks a lot. Thank you. Thanks a lot for the kind introduction and for the invitation. I'm very happy to be here and to meet all of you. I was already here for a couple of days. I had a very nice discussions. And yes, I know that many of you are working on things related to simulation. So I thought that maybe for this talk, which I have never given before, so I don't know how it's going to go, I should say a few words about how I see it, just like my thoughts and maybe some lessons I learned, and hopefully you'll find them interesting, about this interplay between cosmological simulations and perturbation theory, and how one helps the other or guides the other in trying to fulfill these goals for the future, where we want really to either basically make a new discovery or really constrain lambda CDM to a much higher level of precision. So, let's see if it works. Good. So, I think that this is the rough outline, even though the talk is not very much structured as a story. It is more a collection of various things. And I would like to start a little bit saying, why do we, maybe a bit unconventional reasons for why do we think that an analytical approach to galaxy clustering is useful. I will say some things about how we use simulations in an obvious way as a test for these perturbative models. And then I will talk a bit about other things which have to do with covariance matrices, various interesting things where I think that this connection between perturbation theory and simulations is the most interesting, which has to do with this field level comparisons and predictions and how they can be applied in practice. And then I will say a few maybe lessons about forward modeling, which can be even interesting in the non-perturbative regime and for the weak lensing. So this is a set of thoughts and ideas, and hopefully you will find some of them interesting. And if you have any questions, please stop me at any point, or if you want to discuss later, feel free to find me, and I will be here all day long. So let me start by showing this cartoon where I, roughly speaking, put these points as they sit on a nice exponential line, but they're roughly correct. And they show you that the number of observed galaxy spectra as a function of time grows exponentially. And we are basically increasing the size of our spectroscopic samples by a factor of 10, basically every decade. This has been going on for several decades now. And I would argue that nowadays it's a very interesting period in time, because the upcoming galaxy surveys, such as DESI and Euclid, that will deliver their first data within a couple of years, are going to, in this exponential growth, cross this line, which I somewhat vaguely called information in the CMB that we have at the moment, which is Planck, in the sense that the cosmological parameters constrained from these galaxy surveys will be comparable to what we can do with the CMB. And this is interesting because for the first time we have, we're going to have data where with this amazing precision in this different anchor in the late universe compared to the CMB, and then the potential for discovery is really large. So this is a very exciting times. I think that it's not really the number. I mean, roughly speaking, you can think of, if you really want to be very naive, you will compare the number of galaxies with the number of pixels in the CMB. The number of pixels in the CMB is roughly 1 to 10 million. It depends how you count. And here you're going to have something like, I don't know, 30 million galaxies. So they're comparable, even though, of course, it's a bit unfair to compare number of pixels and number of us. But let me maybe show in what sense they're comparable. So you can do a little forecast and ask yourself, how do the contours look like if I use the mock Planck likelihood? In this example, in this paper, what was done is to, like, is there a pointer? Well, it's not. Like, what was done is to basically use the mock Planck likelihood, assuming that cosmology lambda CDM with the neutrino mass, some neutrino mass is of 0.1 electron volt, which is still allowed by data. And then these dotted blue contours are mock Planck likelihoods if you had synthetic sky with the discretization of the cosmology. And then you should focus on the red contours, which are just the power spectrum analysis of a survey like DESI or Euclid-like survey, including all the various redshift beams and the volume and stuff like that. And you can see that these contours are kind of comparable to each other. So in that sense, things are going to be comparable. Of course, some parameters, such as the amplitude of the power spectrum, omega baryon, NS, and so on, CMB measures much better. But for example, neutrino masses are measured better by the large-scale structure surveys, which makes sense because it's a late time effect. And some parameters, such as, for example, omega CDM or Hubble, are measured in a comparable way. And if you focus on these contours, of course, they will have different degeneracy directions. And this is because you're looking at very different redshifts. And basically, this all comes from computing distances, essentially. And then in combination, the error bars are going to be very tiny. Now, our goal, of course, is not only to increase the error bars, but basically, when you increase the error bars in Hubble or omega CDM by a factor of 5 or 10, what you're actually doing is allowing to test much more rigorously any extension of lambda CDM. If there is anything in the dark sector, if there is anything out of ordinary in the cosmology, in the real cosmology, which is not described by lambda CDM, this is the way to find it. So this is why I think this is a very exciting time. And so recently there has been a little bit of a progress, which opened up, I think, a little bit of a new direction and a new outlook on galaxy clustering. And so in the same way as these linear codes, when they appeared in the 90s and early 2000s, they revolutionized a little bit how we do CMB and allowed for the MC-MC chains for various cosmological modes to be done routinely. Nowadays, a lot of progress in doing some perturbative predictions for galaxy clustering and putting all these in the nonlinear extensions of linear Boltzmann codes led to the similar progress where we can now test many models and do cosmological data analysis in a very similar way to what we do in the CMB, but now with galaxy surveys. And here I list a couple of codes that are currently available, and you can just download them and play with them. But I'm sure that I know that people are working on more professional people, like Julien Lesgourg and so on. So I think that there are plans to really make this much more well implemented in the extensions of the linear codes. And so in this sense, we have a complete understanding of the evolution. Let's say if you really want to think in this effective field theory way, you will say that when I start from initial conditions, I can have effective field theory for inflation, understand the long-run degrees of freedom. We know how to do the linear physics around the combination, and this is now completed through this understanding how to deal with the long-run degrees of freedom in the galaxy density fluctuations. So, of course, this is always relying on some assumptions. And because we're trying to compute things analytically, clearly, we do not have control everywhere. And in this talk, when I say perturbation theory, what I really mean is that we are solving perturbatively the equations of motion, which are derived within the framework of the so-called effective field theory of large-scale structure. And I think that Leonardo gave a talk here, if I'm not mistaken, recently. So I'm sure that he told you many details of this theory. I'm not going to repeat it. But here I want to maybe say a few words about why do we think that these things are interesting? So why do we do perturbation theory? Now, usually the conventional answer may be, well, this is because we can, okay? It's very simple. It's it's some kind of formula on large scales. It kind of works, so it looks good. And then we are just rather than learning how to code and write like a big simulation, maybe for some people just easier to do equations. This I can tell is true, at least in my case, but I think there are also other reasons. And I think that if you think about it, I want to maybe mention two reasons that I find rather interesting. At least when we talk about the context of galaxy clustering, we always have some cutoff, basically, where we stop gaining information very significantly. There is still always some gain when you go to smaller scales, but when but since we have like the discrete tracers, which usually in the samples that I was mentioning at the beginning, and in the future surveys will be rather large, this noise. When the power spectrum becomes of the order of 1 over n bar, then you don't gain a signal to noise as k max cube anymore, and you actually stop gaining because the covariance remains constant and your signal goes down. So you can gain only logarithmically, basically extending to higher k. And so if this means that even if you have a perfect model for galaxy clustering, you cannot beat the noise. And this is something that is one thing that you should always keep in mind. So perhaps for some applications where 1 over n bar is large, and this is certainly the case at high redshifts where we have the most of the volume, it may be that perturbation theory is most of the things that we need. So this is one motivation. So it's not only something that we can do, but actually it can be really almost in some cases all that we need. And then another point, which is a bit less obvious maybe, is that in some sense, as we increase the precision of our measurements of cosmological parameters and go to larger and larger volumes, our statistical error bars are shrinking. And basically, we are gaining more and more signal to noise to measure any of the cosmological parameters. And as we do that, the required precision on our theory is also increasing. So it's always a moving target. So for example, I'm trying to plot here some cartoon in which I say, like, for example, what is the typical error bar delta P over P in a simulation compared to, let's say, perturbation theory. And these curves typically look like that. For example, maybe this simulation is 1% precise, more or less on all scales, or 0.5% or whatever it is. And perturbation theory usually can be made very precise on large scales, but very quickly, as you go to high K, it becomes very bad prediction. But you see, it's not enough to say, well, then this perturbation theory is not enough. What you have to take into account also is how much signal to noise you have in the observable volume, because as you go to higher K max and you increase the volume, then basically the relative error bars on your cosmological parameters are improving, and the delta P over P that you need is going down. And then the question is, like, when do you hit this line? Do you, for example, if you're in this limit where you have a relatively small volumes, then the first thing that breaks down is perturbation theory, and simulations are going to improve things. But if you're in the limit where the volume is very large, this may not be the case. So for each probe, for each survey, for each sample, one has to do a little of an exercise to see what is the regime. And it's not obvious that you always gain by having some percent precision or so at high K. Now, there are clear examples, and I've been asked specifically by one of the organizers to mention this, that, like, of course, perturbation theory doesn't work when you don't have separation of scales, because EFT large K structure is designed to work when there is a scale separation. And one such example is weak lensing in the context of photometric surveys, where simply by the fact that you have to integrate along the side, you're mixing like scales in real Fourier space. And then, for example, for the fixed L, you in your observed shear, for example, you have to integrate for various small scales, and then this can contaminate your predictions. And so one exception for this is the CMB lensing. And for example, I'm sure that you saw Matt's papers about that. So this is a little bit of a motivation. And now I want to go through a number of, let's say, little examples that show, like, where are we with this perturbation theory, first of all, and then say a little bit later a few words about how, what are some lessons that we learned, and how can we a bit more creatively combine simulations and perturbation theory. So the most traditional way in which these two things like talk to each other, and this has been done for decades now, is to run n-body or some other types of simulations, and then use them as a place where you test your perturbative predictions. And just as a one of the latest and the most impressive, in my view, example, let me show some results from this so-called Perturbation Theory challenge. It was designed by Takahiro Nishimichi and Masahiro Takada. So basically, they created a huge huge boxes with total volume of 600 gigaparsec cubes, so much bigger than the observable universe. Okay. Which is like basically 100 times the Bose volume, okay? And then they, on the website, they provided, they told everybody that cosmology is lambda CDM with certain parameters fixed, the other parameters are free. And then the question was, given the data, which are measurements from simulations, the challenge was to fit, this was a blind test, to fit cosmological parameters and test whether you can recover the right cosmology. And so here you can see the usual power spectrum monopole and quadrupole. This is all in redshift space with some particular HOD, which is designed in such a way to resemble Bose data. And for example, these are some best fits that we produced. And then you can look at the residual plots and see that actually in each of these k-beams, particularly for the monopole, the error bar is basically 0.1%. So this is the 1% error. So these are very precise data. And if you make any mistake in any of these BO wiggles, or like you don't do things properly, then this can lead to a disaster. So it was a blind test, and various groups were able to recover actually the correct cosmology using different codes. And I think that this is a good based on this perturbation theory. And this was a good test to convince us that what we are doing makes some sense, at least in this limit of very high precision. So for example, what I'm showing here is like the fit of the entire volume with up to Kmax 0.16. This is one of the plots. Where you can see that, like if you focus, I think, on the either green or yellow contours is what matters. You can see that we recover unbiased cosmological parameters and B1, and the precision is 1% or better. So these are very precise measurements of cosmological parameters, and you can see that things are unbiased. While on the right-hand panel, the exercise was to basically rescale the volume to the DESI volume. And you can see that, for example, for the DESI volume, even if you go to Kmax 0.2, 0.25, 0.22, and so on, the cosmology remains unbiased, which means that in principle, if we had the data at the moment, these are the kind of error bars that we would be able to obtain. There are some caveats to this, but let me not spend too much time on that, except maybe I want to emphasize that you can already see that the error bars are almost saturating, and this is because there is a shot noise. And I think that this is what I was saying at the beginning. Then going to higher Kmax is not really maybe buying you much. Yeah.
Just a short question related to this. So you say saturating, but these Kmax are relatively close together, right?
Yes. I think that you have to check.
Is it really saturating, or is it just?
If I remember right, it was not going as fast as Kmax cube already, because I think that around 0.25 or so for this particular sample that was in this box, we were seeing that the shot noise becomes almost as big as. Now this may change for ELGs, of course. This is a bit different. This is a bit of an exercise which is using the Bose like luminous-side galaxies like sample, just rescaling the volume. And another caveat, which is very important, is that the perturbation theory challenge was designed to have omega baryon, omega CDM fixed, instead of having only a prior and omega baryon. Then the contour orientation is different, and I think that if you were to do omega baryon, the error bars will be tighter. So this is a little bit different compared to maybe the real analysis we would do. But I think that you already start seeing that there is some saturation.
For Euclid, it will be similar.
For Euclid, I think it will be very similar. Yeah.
I thought that you can get around if you use multiple tracers. Okay.
If you use what?
Multiple tracers.
Multiple tracers can remove the shot noise, I think, on large scales more than on small scales. Because I think that's what you want. Are you talking about something like a mass weighting, or really talking about small? Yeah. If you cross-correlate them, I think that it is true, assuming that the noise, that comes for both of them is uncorrelated, which might not be the case because but the shot noise is not purely because you see the shot noise somehow tells you whether in the region of space you form a galaxy or not. So for example, if you do an exercise, I would imagine that where you keep the long wavelength fluctuations in your initial conditions fixed as a realization, you just vary short scale modes, you will get the different realizations of the galaxies. And there will be galaxies somewhere or not, depending on these small scales. And I think that this somehow tells you that a part of this shot noise, at least, is this basically averaging in a sense over short scale realization, and that will impact all traces. So I think that there is always some irreducible noise in the multiple traces.
Correlation of two different samples, you don't get the shot noise distribution in the signal, but you do get in the covariance.
Yes, I would be very right. I would be very surprised if it goes away. I think that this is hard to beat, but also I think that then there is also this question: can we really find two separate samples and so on? So anyway, this is one example of this traditional interplay where you really say simulations. I believe I just use them, even though maybe they're not perfect, and maybe all the microphysics, I don't really know if it is true, but at least it's a playground to check these perturbative methods. And this is very useful because it allows us to, in a sense, calibrate how far can we go with perturbation theory, what is the K-max that we can trust, or maybe alternatively, I just want to say maybe another approach would be to somehow calibrate how big is the theoretical error that you're making by simply looking at the difference between your best fit model and the real data as you go to higher K. So in a sense, you can estimate what is some delta P over P. And of course, on large scales, this is going to be a very small thing. So you're predicting the power spectrum not very well. As you go to smaller scales, this of course grows. And using some Gaussian processes, for example, you can marginalize over all possible shapes of your theoretical prediction within this envelope. And if you do that, you can basically find out that the likelihood for the data analysis is the same as before with slightly modified covariance matrix, which now includes this theoretical error. And this is very useful because it's an alternative to just trying what K-max works, because you can go to any K-max. You will simply naturally stop gaining information where your theoretical uncertainty that you calibrate from simulations basically becomes big enough compared to the statistical error bars. And you can see what I'm talking about in this plot here, where what we did is to use different K-max and see how the error bars on various cosmological parameters depend as a function of K-max. And you can see that, for example, at the beginning, everything is unbiased. But eventually, you start being biased if you're using the wrong one-loop theory for matter power spectrums. It's a very hard to make a perfect prediction. And maybe accidentally, at some K-max, they work again, but it's a pure accident. You're already biased in these scales. However, if you use some kind of a theoretical error prescription, you go to whatever K-max you want, this will be the final answer. So you never get biased. It's simply error bars will saturate at some point and to their basically optimal values, and you don't have to do all these exercises. So this is maybe a bit more precise way in which we use sometimes simulation to get some inference of how well are we doing in perturbation theory. Yeah.
So why do they saturate here? There is no shot noise here, right?
There is no shot noise, but you see in the covariance matrix, now your full covariance in this case will be the data covariance, the usual one with the shot noise and everything. Sorry, in this case there is no shot noise. You're right. But then there is also this CE, which comes from marginalizing over all possible shapes within the band of your uncertainty. And this is a quite general thing. Imagine even if you have a simulation whose error bars are growing, and maybe at K of 0.1, it's very precise, but at K of 5, it has a 1% error, at K of 10, it has 5% error, and so on. So there is some band, and you're not entirely sure where your prediction lies within this band. You should marginalize over it. And this is a very simple way to do it. And then basically your covariance has this extra piece, which is big enough such that when the cosmic variance error goes down, eventually you hit the second piece, and then you saturate. You cannot improve.
What did you assume here for the theoretical error?
Okay, so the only assumptions that you have to put in this Gaussian process is that how big is this envelope? Like, what is the relative error that whatever method you're using has, and how smooth curves do you want inside? Like, for example, we know that the power spectrum doesn't have crazy wiggles. So it cannot be that all these points are independently varying. It has to be some level of smoothness. These are the only two parameters. Yeah.
But this
This is what I was saying, that we calibrate this thing by basically fitting perturbation theory up to some scale where we will trust it, and then for higher case we look at the difference of this best fit and the truth. So it gives us some idea about how much we are off compared to.
That's right, but if you would use simulations, it would be different.
It would be different, exactly. So simulations in this case will give much tighter error bars, because for matter they're super precise. There is no question. I mean, if you repeat the same exercise, for example, for weak lancing, then it's a bit of a different story. There, for example, you may say, well, and I go to small scales, these uncertainties from different hydrocodes are producing some band of uncertainty, and if I marginalize, I will see the similar saturation of errors. And then the question is, like, yeah, how much? Like, it's a bit of an estimate, but it is yet another way to use simulations to infer how well you're actually doing. And I will just briefly say that, like, given that we have this confidence that for at least for the Boss error bars, our predictions are good enough, and even for DESI probably, or Euclid, but for Boss certainly good enough, we can do the full shape analysis in which we vary all cosmological parameters within lambda CDM or any other. There are many extensions, and like in a series of papers and many others that follow up, including other observables such as the bispectrum, higher order multiples, some estimates of the real space power spectrum on small scales, and so on. You can basically measure cosmological parameters. And what is an interesting thing is that, and it was not done before, is that if you do this, again, there are some parameters which are not very well constrained by Bose compared to the CMB, but there are some parameters like Hubble parameter, for instance, or omega matter, where the error bars are very similar to Planck. And it's an interesting thing, and it's a good confirmation that these two very different data sets, which have very different systematics, different observational strategies, that are at very different epochs in the history of the universe, give consistent data, even though, of course, we are assuming lambda CDM in both of them, so they should, if there is no any systematics. And in a sense, this is a test that it doesn't seem that there is some obvious problem in either CMB or large-scale structure.
That's a statement on the local measurement.
It is not much of a statement on a local measurement. I think that since we always assume lambda CDM, we expect to find the same answer. Imagine that the cosmological model was different, then also the Bose contours will shift. Now, the good thing about this is that actually when you apply the full shape analysis to various like proposed models, they're much more. Yeah, no, I understand. But like, I think that it's a bit different because these are still indirect measurements, both of them. And even though it is done at a low redshift, it still assumes early universe history and everything. So I don't want to compare it to the local measurement. I think that the only thing that we can honestly learn is that the CMB and large-scale structure give the same answer, assuming the same model, which is good. At least there is no major issue.
But in some respect, this is an early universe.
This is, yes, it is the BAO plus equality scale, omega matter, everything is folded in. I think that in this sense, it's in this indirect. I don't know if it's early, because sometimes it's confusing because it's a late time data. But I think that once you set initial conditions and cosmological models, the entire evolution or fluctuation is fixed. So whichever way you intersect in a single slice or in the light cone, it doesn't matter. You're doing indirect measurement because you're fitting the global model to your fluctuations. So it's different from measurement by definition, which is these local direct measurements.
Then I think also through nonlinearity is there's potentially more information in the late time, even though it's similar. Okay, the same is like the initial condition and evolved, but if you still assume the homogeneous and isotropic background and evolve it to particle structure, then you can, I mean, break degeneracies or whatever, but the dependence on like BAO enters differently into our spectrum, bispectrum stuff, and so it's a bit, you're maybe testing a bit more than just the same initial condition.
Yes, I think that at that point, it's really a matter of error bars, how much galaxies you have, and so on. At least, I mean, for this, I think it's interesting that Bose, these are data from 2014. Back then, they could have done this measurement, and at the time, there was no Planck 2018, so they will be even maybe better in terms of the Hubble parameter. This is just to say that it's a bit of a different, like maybe, yeah, it's useful to have this slightly different approach. And these are boss people, like using a remote control to. I'm joking. It's like, in any case, I think that of course the focus back then was always on the BAO. It was a very important thing, and I think that somehow we forgot a little bit that we can also do other things. But I think now this is becoming fashionable again. Now, related to this, like power spectrum analysis, I may want to share one lesson that I think that I was always a little bit puzzled about it, and there were various intuitions, but perhaps I can show this, which again maybe gives us a little bit of a hint how can we use simulations for the covariance matrices. And I want to, here I'm showing up this a plot from the paper by Jay and Raman, like about the covariance matrix. What they did is to compute the analytical with the covariance matrix, including nonlinear corrections and the mask. And they're comparing that to the Gaussian approximation. And you can see that in the cumulative signal to noise, for example, in the monopole, but also in the quadrupole, there is a big difference whether you're using Gaussian covariance or the full covariance. Now, this is the usual intuition. If you use the simple Gaussian covariance, you expect that you're going to underestimate your error bars, you overestimate the power, constraining power. And the intuition was that because of this, like we have to be careful, and this Gaussian approximation is not good to be used in the Fisher forecast and so on and so forth. However, there is another intuition which tells you that there cannot be much difference between using Gaussian or non-Gaussian covariance, and that this cumulative signal to noise is not the real thing to look at, because what cumulative signal to noise really measures is the amplitude of the fixed shape nonlinear power spectrum. So you're really asking, if I knew exactly the shape of the nonlinear power spectrum, how good error bar would I have on the amplitude? And this is what this signal to noise is. And indeed, if there's only this one parameter, there is a difference. However, in any realistic analysis, we always marginalize over certain, let's say, bias parameters, nuisance parameters, or these theoretical errors like that I was talking about. And if you imagine that you linearize your theoretical model and you have some, again, like envelope which multiplies P of K, you use a fraction of how big are these effects. For example, in perturbation theories, usually there is a K square P of K type of terms, and you marginalize over these nuisance parameters, you're going to generate a covariance, which is going to be the old covariance, data covariance, plus something which grows at K, at high K. So what you really have to ask yourself, whether the non-Gaussian corrections in your data covariance are bigger or smaller than these things. And then you will get the right answer. And so usually it happens that this always dominates by a lot. And so what happens at the end of the day is that all these details about nonlinearities that affect the covariance matrix are not so important. So you're basically dominated by this marginalization in the covariance for the cosmological parameters. And of course, on large scales, what is very important is to keep the mask appropriately, because it couples all Fourier modes. And you can check that in the real data analysis. So contrary to the expectations that the error bars will change, actually they don't. This is like applying Pechy-Moggs or analytical covariance to the Boss analysis. However, what it does happen is that, and there are similar plots in the paper, you can take a look. Even if you use a Gaussian approximation, you get identical error bars. What does happen, however, is that there are small shifts in the posteriors compared to any analytical prescription compared to the Pechy-Moggs. And I think that one curious thing that we learned is actually that this is because there is a noise in the Pechy-Moggs. Even if you have 2000 realizations for a data vector which has roughly 100 beams, this seems not to be enough not to have some fluctuations in the best fit parameters, which is a point something sigma. It's not a big deal, but you may want to keep this under control. So, so in other words, it seems that really, like, we don't have to worry. One lesson here that we don't have to worry so much, at least in the clustering, about small scale covariance. And what we really need is maybe more Moggs, which are a bit more sloppy. So that is like one, I think, interesting lesson that came out from this exercise. So how much time do I have? None. Okay, so basically half an hour.
20 minutes.
20 minutes, okay. Okay, so in the 20 minutes, I don't think that I can cover everything, but let me say a few words about now something. So far, this was like mainly related to the endpoint functions and power spectrum analysis. I could have told you similar stories about the bispectrum and so on. But I think that there is something interesting that we can do. Like if you try to maybe aim to somehow match this benefit of understanding much more what happens on small scales from simulations, while keeping this precision or this robustness on large scales from perturbation theory. And I think that this, of course, people have been trying and they were succeeding in many examples. For example, COLA is one example where there is some interplay between what you can do perturbatively and then with the n-body simulations, but it's for dark matter. I think that here what I would like to ask is like, what can we do really for bias traces in the redshift space directly for what you observe? And I think that really the question is how can we exploit simulations better, or like somehow smoothly merge the two approaches better. And I'm going to say a few words about, first of all, doing the test for perturbative models at the field level rather than looking at the summary statistics and why is it interesting. The second thing is going to be how can we use it to basically provide some estimates of these nuisance parameters which appear everywhere in describing the galaxy density field, and then also say a few words of some ideas how to maybe smoothly connect to the nonlinear regime. Now, in all this, one major challenge is that usually we don't have access to many very large volume high resolution simulations. Obviously, like maybe you can make one box, but making many is not very easy. And if you really want to have something which is like complicated and contains a lot of non-trivial astrophysics, usually you make high resolution small simulations. And then one of the main, but on the other hand, perturbation theory is valid on large scales. And then there's a little bit of a challenge how to connect really the two and how to test the two. So I will say a few words about that. Now, first of all, I want to tell you a little bit about this very simple algorithm for how can you decide to make perturbative maps. So it is really a small modification of Zeldovich. So it is very easy to implement in practice, and I'm sure that all of you can easily call it up for yourself. And the way that it works is that you go to a Lagrangian space, and rather than moving uniform grid, meaning that each particle on the grid has a weight 1, and you just displace it with Zeldovich displacement, which would be the usual Zeldovich. What you do is to compute this Lagrangian, if you want, bias operators of Q, which can be delta of Q, delta square of Q, tidal field at the point Q, and so on, and then displace those by Zeldovich. This is what we call this shifted or displaced Lagrangian operators. And here I'm writing some general form in redshift space. You can do that, of course, in redshift space. Now you can show that, I'm not going to do this, but you can show that this really is boiling down to the same thing as essentially at the end of the day, you're always going to have some Eulerian bias expansion. And you can show that this really boils down to the usual Eulerian bias expansion with the so-called infrared summation, because you have these large displacements taken into account at the one loop level, whatever you need for, let's say, for the one loop power spectrum, 3-level bispectrum. And a big advantage of being able to make a map and compute perturbative map and compare to simulation rather than just doing the power spectrum is that, first of all, since you can choose the same initial conditions, you're going to have the complete cosmic variance cancellation. So these are going to be basically the same realizations at the end. You're testing all Fourier modes. So basically, when you compare the maps, all Fourier modes have to agree, not only some summary statistics. And these perturbative maps also allow you then to compute any other statistics other than the power spectrum. So we can do the power spectrum computation or bispectrum computation, perturbation theory, but from this full field, you can compute whatever else you want. I'll show some examples. So this actually works rather well. I mean, even a simple perturbative map with a few nonlinearities in it usually predicts the true nonlinear field quite well. And in a series of papers with Marcel and Matthias and others, we're testing this in real energy space for dark matter halos and galaxies. And for example, you can here see on the left-hand side, there is a real space simulation with a certain outcome given some initial conditions for, let's say, dark matter halos. And then you have the real space perturbation theory model for the same initial conditions. So you see, these two fields are very similar to each other. They have this large scale characteristic are the same. And if you look at the differences, if you look at the difference between the two, this difference or power spectrum of this difference is perfectly compatible with flat shot noise. So basically, up to the fact that we have a shot noise, we cannot distinguish these two fields. And the same thing is true in redshift space, which is like the other two panels. And again, you can see that the large scale features are identical, but for example, on small scales, we would generate, of course, in the real simulation, very extended fingers of God, while perturbation theory doesn't know how to do it. So the agreement is a bit worse along the line of sight, but again, it's perfectly compatible with the noise that you expect along the line of sight, which is, of course, now mu dependent. So up to the usual noise levels that we use to add to the galaxy clustering in redshift space, everything seems to be fine. A similar example done with Aurel and Robert and Andre here is for, let's say, neutral hydrogen. We just wanted to see, because it's a little bit of a different tracer with much higher number density, essentially, and it's like a really continuous field rather than a set of discrete tracers. What happens if you apply the same methods and compare it, for example, to some hydrodynamical code, such as Illustris TNG 300, let's say this is the biggest box, and you can see the neutral hydrogen map in one slice at redshift 1. And now if you make perturbation theory map with the same initial conditions and ask yourself, how does it look fitting for a few bias parameters, the same ones that we have in the one loop power spectrum, then you will get something like that. So you see the difference between perturbation theory map and the truth is visible. There are small differences you can tell by eye, but all those are compatible with the expected value of the shot noise. And in fact, if you compute the power spectrum of the simulated H1, the theoretical model that we are using, and you look at the power spectrum of the noise of this residual difference between the two, you see that everything looks good. The model power spectrum looks fine, and the noise power spectrum looks flat. It is compatible with 1/m bar up to very high K. So, in other words, these maps are not somehow so complicated. At least for their rough description, we can use a simple minded formula, and we can go quite far with it. So this is one nice lesson that we learn from all these exercises. But of course, the point is not only to test things. I already said that we use simulation to test things, but now we would want something more. In all this, for example, analysis that we have in large-scale structured data analysis, we are always pretending that we know nothing about our tracer. For example, when we do the Boss analysis, we put these B's to be anything, basically, or like clearly we know that the B1 for Boss Gauss is around 2. It cannot be 5 or -1. I mean, this clearly is not the case. However, we have very broad priors, and we're trying to measure all these nuisance parameters from the data and marginalize over them. So we are paying some price on cosmological parameters for pretending that we know nothing about this, which is not true. And in fact, in simulations, we do have some priors on these parameters. We do know, or we can maybe investigate how big are the uncertainties on these things. And now the question is, like, how can we somehow combine the two? I want to come to that. And these field level methods are, I think, very nice to do this, because in principle, even from a relatively small box, you can measure, because you don't pay the price of cosmic variance, you can measure very nicely what are these parameters. And then what you may want to do is to try to even use smaller boxes, which are maybe people design with various cosmological parameters or astrophysical feedback, which are usually a few tens of megaparsecs on the side, not larger than that. And there are many of them. And of course, you cannot apply perturbation theory modeling there, because simply things are too nonlinear from the very beginning. But however, you may want to do some kind of like iterations to come to the similar situation that I described before. And one idea is to really take a bunch of these small hydro boxes with various cosmological and astrophysical parameters, calibrate some sort of HOD on them, or try to understand, because you don't want to be super precise. At the end of the day, you want to estimate some scatter. You don't want to make maybe a perfect prediction. So calibrate them in some way, which can be then used to populate like intermediate high resolution dark matter simulations, which are easier to make. And then play the same game as I described before of basically making perturbative maps for those, measure the bias parameters, and do that for many cosmologies, many realizations of the astrophysical data. And you will get how these bias parameters for the perturbative maps are scattered depending on these choices of different cosmologies and Nuss's parameters. And then you can go to like larger boxes and make big perturbation theory mock data that you can use, for example, for the covariances because they're precise enough, or you can simply play with them to see how well you can constrain cosmological parameters and so on. So this, I think, is something that has never been explored very much. We don't really know, for example, if you change, it's a bit hard to say if I go and change particular feedback in my hydro code, how B2 or a tidal bias is going to change. And I think that is very important to know, because if you have any hope to then use simulations to improve significantly our measurements on cosmological parameters, regardless of perturbation theory. Here, perturbation theory just provides one simple example on large scales, which we know it is okay to give you a target for simulation. How well do you want to get these numbers right? So even if you don't want to do perturbation theory, it's nice to know this scatter, because if you have any hope for simulations to be very useful, what is going to happen is that when you vary astrophysical parameters a lot, maybe the bias parameters will not change much, or they will change in a way that they're very degenerate with each other. So there will be something much more constraining than a simple-minded case where you say bias can be anything. And I think that would be very interesting to explore. We don't know what is the answer. People may have different intuition, but we really don't know. It would be nice to check.
But this is sorry for galaxy clustering, right? Because of the K.
It is also for galaxy cluster, because imagine that even on very large scales, if you change a little bit the star formation rate, B1.
That's right.
Yeah.
But, it's essentially scale free, and most of the cosmological information comes from the DAO.
I think that, for example, sigma 8, neutrino masses, any omega CDM comes from the shape, the quality. So I think that there is some information. Yeah, and you're competing with these biases, so you want to nail them down. Yeah. If you do the linear theory forecast up to same Kmax, you get a factor of 10 times better error bars, for example, for Bose volume or something like that. So we are paying a big price. So this is, I think, one concrete way to do this interplay between perturbation theory and like you see, you're using it in a creative way. It's not just comparing or like. I think that it's a way to really extract some information from what we have to basically learn a bit about what can be done in perturbative framework, but also like is there some non-trivial input that small scale simulations are giving us that we are not aware of? Because on one hand, we have some bias parameters and we don't know how to connect them nicely to more physical parameters which enter the galaxy formation and so on. Now, another way in which you can use this is to say, well, for example, here I was showing like how this residual noise looks like, and I was showing it has a constant power. But for example, if you subtract this constant, you're going to see that actually here there will be some small residual which then decays very fast, which is in a sense the true 1/2 term. These are the true small scale nonlinearities which we are not capturing by perturbation theory. And this can be done, of course, for dark matter as well. If you do the same plot for dark matter, there will not be even the shot noise. You will have the same kind of plot, and there's some k to the 4, like a small scale feature, because this is the noise that you expect in the dark matter case, and so on. So in some sense, you can take a look at this and say, let me then use even relatively small boxes. I don't care about this big fluctuations which are induced by realization on large scales, to basically calibrate this error, either for dark matter or for bias tracers in relative space. And then your nonlinear power spectrum is going to be your perturbative model, which is easy and simple to compute, plus this uncorrelated power spectrum of the noise that you're going to calibrate from simulations. And the good thing is that this doesn't have features. It is in a small range of scales. You don't have to fit BA or anything. So it's easy to fit. It doesn't have much features, and probably it doesn't have super strong or super complicated, let me put it this way, cosmology or Nuss's parameter dependence. It may be smooth. So I don't know, but it would be good to check. You see, we don't know these answers. It's a bit unsatisfactory that I cannot tell. I mean, like I'm really curious to see that. So for example, that would be another way. And then you can get some, let's say, simpler version of the hell fit, where you don't try to fit for the whole thing, because this is, of course, noisy. There is no need for that. We know that perturbative description is fine on some scales. So let's do this hybrid thing. And I think that this can push us further than what we have at the moment for dark matter, for weak lensing, but also for galaxy clustering. And ultimately, one may even dream to do some sort of machine learning where you really, from the initial realizations, looking at the residual things, you learn like where it will be the trouble, where there are big overdensities, and somehow make a residual map which looks like realistic, such that you can do this exercise at the full field level rather than just for the power spectrum. But that's something that I don't even know how we will do, but it's maybe interesting to think about. Okay, so let me just then mention something about these alternative statistics. Of course, people always talk a lot about, not a lot maybe, but there are many people who are interested in things beyond the power spectrum or bispectrum. And for example, in the same paper where we did this neutral hydrogen, we were checking this simple summary statistics, which is just simply counts in cells, to see what kind of distribution do we get if you look at the perturbative map or the truth. And you can see, as long as the cells are not very large, the two, very small, the two agree rather well with a simple Gaussian like scatter in the error between the two, all the way up to K of 5 megaparsecs, which means that whatever is your summary statistics up to this scale, if you look at the voids or you look at whatever else or counts in cells, you're going to find the same thing in your perturbative map, and you're going to find the same thing in like simulation. And this is encouraging, but also I think it's a way to explore much more and much better and in a much simpler way what do these alternative statistics really measure, and I think that how much they're correlated truly with the power spectrum. And I think that this is something that will be it's very worth exploring, and it would be good to have some better understanding of what we have at the moment with various contradicting claims in the literature. So this is yet another application. Okay, since I'm running out of time, I wanted to say something about perturbative forward modeling. This is yet another, I think, interesting, there are some interesting lessons that can be learned for simulations from this perturbative forward modeling. I can just highlight, because you don't have to look at the formulas, but I can just highlight that if you do this perturbative forward modeling, what you would really do, just for those of you who are not familiar with it, is that you're trying to fit the entire density field, varying all possible phases and amplitudes of initial conditions. It's a humongously complicated problem, but the claim is that you always recover the full amount of information in all endpoint functions and like various summary statistics beyond the simple power spectrum or bispectrum. Now, I just told you in the previous slides, and I showed that a simple perturbative map with only cubic terms in the nonlinearities is already almost good enough to predict the true nonlinearities. So you don't have to go to very high orders in perturbation theory to make these predictions. And then you can ask yourself, well, if this is the case, if I have to keep only cubic terms, is this analysis really different from simply calculating one loop power spectrum and three-level bispectrum? And it turns out that the answer is no. You can really, in perturbation theory, for some simple examples, you can compute exactly the posterior in terms of the data that you would get if you do the full forward modeling analysis. You can, for example, then see what are the optimal estimators for, let's say, the amplitude of the power spectrum and what is the variance. I'm just quoting them here, but you don't have to look too much into equations. And it turns out that they're exactly identical to what you get from the power spectrum and bispectrum analysis. Of course, because you were putting those nonlinearities in, this is the only thing that you will get out. And all these voids, counting cells, and so on should somehow be encoded in the bispectrum. It's a very counterintuitive, but this, I think, is a very simple exercise where you can check explicitly that you have the same constraints. Because the three-level trispectrum requires also quartic fields, I think. Or maybe, no. No, it's okay. I think it's still enough. Yes, maybe the three-level trispectrum, yeah. I think that it's a bit inconsistent. Maybe it's fine. It is okay. You can keep it. Yes, maybe this is right. Yeah. Anything that you can build with only cubic things and nothing more. And this is exactly what happens. So it's a way to like somehow. I hope that this paper will come out. It's like we're writing it for years now, but like I really hope that like this example, once you take a look at it and the paper is out, you will convince yourself that somehow this intuition that there is so much more in the nonlinear field is not maybe entirely true. And so we should test it a bit more rigorously. And I think that some of the methods that I described before would be an interesting way to do it. And so let me just finish. Can I have 1 more minute? Saying that this theorem that you get always the same amount of information is true, assuming that the nonlinear scale is the only relevant scale in our universe. That whenever we talk about perturbation theory, we have in mind the variance of the density field is the only expansion parameter. We know that this is not the case. For example, there is the velocity dispersion, which affects the BAO, but that is well understood and we know how to deal with it. But there are other less known examples where there are new large parameters in perturbation theory, which are not related to the nonlinear scale, but they're related to the infrared scale, either in your power spectrum or the size of the universe or the size of the volume and so on. And if you, for example, to find those parameters, you have to look at a very specific correlation functions. For example, this one, where we have K1 minus K1 and K2 minus K2. And this is exactly the covariance matrix for the power spectrum. So in the covariance matrix for the power spectrum, there is a very large contribution, which is dominated by this type of integral, which is not the variance of the density field, it's the variance of the square of the density field, which can be very large, even when the variance of delta is small, depending on the shape of this power spectrum. For lambda CDM, it's a borderline case. It's a biggish number, and it was known for a long time that this term is dominating the covariance matrix on small scales. So it's not nonlinearities on small scales. It's really this very long wavelength modes which contribute most to this integral, which are being exchanged between the two power spectra that you're measuring. So in other words, the large fluctuations, the small fluctuations in delta, when you square them, can become large fluctuations in delta square, and they're modulating short scale power spectrum to cause big scatter in the measured data points in each realization. So you think that your covariance matrix is big, but it is only because there's some modulation with the long wavelength modes. And this is very similar to what happens in the case for local non-Gaussianities. If you remember, the simple estimator for the bispectrum doesn't work. You have to modify it. And also here, there is a way to modify the estimator to make it more optimal to get rid of this problem. And that, I think, is something which is very interesting, because this is going to be, I think, very important for the weak lensing, where you go to very high K for matter. Then I think this effect gets exaggerated. So basically, most of the covariance on small scales is going to be just that. And if you measure simple responses, which are quadratic responses, basically you see how the short scale power spectrum responds to the long wavelength delta square, you will be able to design a more optimal estimator, which perhaps can lead to a tighter constraints on S8. This is something that I'm very much curious to see, and I think that it will be interesting to check. So this is just to conclude, one other example where you now see, by looking at something inspired by perturbation theory, we can get some ideas about what to do with in the nonlinear regime and the simulations. Okay, so I think that I'm already running out of time. I already said all these things. I will just leave the slides here and stop the talk here. Thank you.
Marco, questions? Jump in. Yeah.
Forward, yes. Maybe someone else. Otherwise, I have a short question. So you talked a lot about Bayesian nuclear spectroscopy, but we have photometric galaxies launching way more galaxies.
Yes.
And what would be the approach there? I guess.
I think that, as I said, I think that if you're talking about galaxy lensing, I believe that still something can be done, particularly if you cross-correlate like lensing and spectroscopic samples, because you're collapsing along the line of sight the integrals for a given redshift. In that case, I think that things can be done. We haven't tried very hard, but now if you talk only about photometric surveys alone by themselves, I think that there is nothing wrong in applying perturbation theory to anything that has to do with the galaxy clustering. You will just have to smooth, of course, along the line of sight, put some kernels and so on, and be a bit careful about these integrals such that you don't pick up too much contributions from small scales, which you wouldn't do probably anyway if you talk about galaxies, because they're still, even though the number densities are higher, you may think that you can still be fine. I think that the difficult part for me to see how to go around is this lensing part, really, kappa. That is hard to get from any perturbative treatment. And then doing some hybrid thing where you do like on the level of the power spectrum, like galaxy kappa thing, like that, I think where you use perturbation theory for one thing and some emulator for the other is a bit hard.
So
I think that is, yes.
We have emulators, we have tools from simulators.
Yes.
But the galaxy clustering is the thing that worries me the most, because
I think that at that point you have to go and do something like this. So you build your emulator, literally doing what I said here. Do something that will be perturbation theory on large scales, but then on the map level, so that you don't have to invent. Because sometimes you will not, for example, the Hello model is a typical example. It doesn't conserve mass, for example. It's a bit, because you're a bit inventing. So here, everything will be fine. You would just calibrate this small scale through one Hello term, and you will do it for kappa G. And I think that, or GG if you want. And I think that this is the way, because the noise will be lower, you're right. And you have to be a bit more careful about this part. It will pop up a bit more clearly, but I think that calibrating that this way would be the best way I can think of.
You calibrate it with HOD or
not even HOD. You literally do perturbation theory on the map levels, like do this analysis, and then look at the residual noise, and just like fit this residual noise as a function of cosmological and galaxy formation parameters. It will be hopefully some smooth function. So
the residual need to compare to something which would be
to the simulations. Okay, what would be the simulations? The same ones you use to convince yourself that weak lensing is under control.
Actually, a couple of questions. One for the covariances. Not really sure. So you compared basically the Pachimok's covariance with Gaussian covariance.
Yes.
The same.
Yes.
Constraints and cosmology.
Yes.
And then you conclude you need more.
No, it was not. It was not really this. I think that the fact that they're the same. So the number of MOCs that you have can affect two things. One is this Hartleb factor, where you have to. You typically overestimate the constraining power, and you have to inflate the error bars a little bit. And for that, this number of Pachimok's is sufficient. Clearly, there is no Hartleb factor. It's one. The error bars are the same. But what the finite number of MOCs can also do is to shift randomly your best fit cosmological parameters.
Understand, but why the constituent is not like we can just use Gaussian covariance?
Well, because it's a bit difficult to compute, because this Gaussian covariance still has a proper mask put inside. So it's just a little bit of a pain. I can easily do it on a simple Zeldovich field, put a mask and measure the covariance. Then there will be no this issue. You can generalize the Zeldovich field so easily. So it's in this sense, sorry. Yeah. It's just maybe simpler to deal with the mask when you have the field than just really computing everything. It's very, very complicated integrals and stuff like that. But it's just a matter of maybe practicality.
The other question moment about the theory errors, which I
Uh-huh.
think is very important, but typically I find nobody like speaking about it or using it right in the
no.
spatial analysis. So like,
I
what's your take?
I think that people don't like it because it inflates the error bars. Yeah. If you do an honest work, it will not look good. So that's the reason. I deeply believe that. So we did check that in various data cuts. For us, it's always the same, using or not using. Like we made sure that it's okay. But then I don't know. That's not very. Yes. Then we would see, yes, that there we were checking K-max, we were putting some estimated theoretical error, we were like seeing, and we saw that everything saturates around the same K, where you start seeing that the fit doesn't look good. So it goes like a two loop, basically. You estimate how big is two loop, and this is a rough estimate, but you can see that everything is coincides. Like if you go to a certain K-max where the chi-square becomes bad, or you start seeing the shifts in your posterior, or you start like being saturated by theoretical error, it's always a similar case. So it somehow indicates that everything is consistent. So
Yeah, I was just gonna comment. So, yeah, typically what we'll do is, so from simulation, you can kind of get a good guess of what K-max will be, say power spectrum, bispectrum, and then it depends if you're doing, tree level or one loop. And then you can add in these two terms. It's a bit of a, I mean, you should really put the error in covariance and stuff, but a kind of an easier way to do it is then do your analysis, but then add in some of these representative two terms with some free coefficients, redo the analysis, see how things
change,
And
yes.
You're a bit more confident that the K-max found in simulation is really truly unaffected by the higher order terms. And so you can look at it's mainly the shifts in the central values of the fitted parameters.
That's not only perturbation theory, that's valid
For anything. For example, with Elizabeth Krauss, we applied for the LSST forecasts and like including some baryonic feedback uncertainties. And what we found is that you degrade the error bars a little bit, but then you're unbiased. And this is exactly what theoretical error is supposed to do. And I think that you find exactly what you need. Yeah.
Any other questions? Maybe for students? Well, any other questions from anybody else? But anyway, Marco will be around.
I'm around the whole day. So
SA tension. You have SA tension in your boss scenario.
I don't know, to be honest. Like there's so many of these boss analyses that I don't like. This was the old one. I mean, here there is no SA tension, but like I think that it depends. I think that what it turns out to be true is that this SA tension depends a little bit on which data sets you combine. Like if you do the power spectrum, bispectrum, which scale cuts, and so on, and also what kind of priors do you choose, or how do you treat priors? There is a little bit of a prior volume effect issues. So I think that it's always between 2 and 3 sigma. So I don't, yeah, it's a bit.
I think you have more recent analysis, right? Than that plot.
Yes, this was the first one. Yes, I think that including all the bispectrum multiples, it went a little bit.
I'm not saying it's a big
yeah,
tension,
there is always, yeah, it's very mysterious. I think that like wherever we look at, you see that there is a little bit lower clustering amplitude. To be honest, I don't know what to think of it. For example, even the full DESI sample cross-correlated with weak lensing, which was done by Martin White and collaborators, shows also like lower S8. So I don't know. It would be fun to see what happens when. I mean, for sure, we see that in the MOGs, which are much more precise, that we are not biased. It's not like error in the pipeline. It must be either some issue, maybe with some prior volume effects, or there is it's a fluke, or there is a real physics, new physics, and it's fun to see. Yeah.
I have a curiosity question about it.
Okay, so sure. Let's see what they wrote. Yes.
Maybe I missed it, but what's the reason for the second one? Like why simulation knowledge is not added into the theoretical model?
So you mean like here? Also, do not incorporate any knowledge. Well, because we don't know how. I think this is what I was saying. Imagine that, let's say, I know Paco always tells me camels, camels, camels. So I always ask him, like, can you predict bias for me? He says, no, it's too small, the volume. So you see, like, we know how to vary hydrocodes, we know how to change things, but we don't know what does it mean for B gamma 2 for a tidal bus. And usually when the way that people measure these biases is to go to very large scales, the large boxes to separate universe or something like that. But you need a large box with a full hydrocode, and nobody, even Paco, is going to run it for you. So I think that, like, we don't just know how to do it. And a part of my discussion was that I was proposing this, like, method where you, like, do various calibrations to go from one kind of size of the box to another one, to the perturbative maps, which should circumvent some of these problems. But it's very important to know, because it's one thing if you have, let's say, two biases and the simulations tell you it can be anything. It's another thing if in the projections the error bars are similar, but it's a very tight prior like that. And which one it is, we don't know. And I think it's a very urgent to know, because the data is being collected as we speak. I think that from observations you can measure some things, but the question is, like, if I put some prior like that, and I'm rather confident it's correct, maybe is the matter between winning or not winning the Nobel Prize. So if this sigma 8 is true, so you see, I think that we are a bit too relaxed, I feel, about this about these things. Okay. Thank you. Thank you, Alex.
For all the people that signed up for lunch,